In this final section of chapter 2, we're going to start taking a look at polynomial and rational inequalities. And so those are literally the only objectives in this section is to be able to solve polynomial inequalities. And then secondly, we're going to take a look at how do we solve rational inequalities. So what is a polynomial inequality? So we have a polynomial function, and we're trying to look at where it's going to be either greater than or equal to 0, less than or equal to 0, greater than 0, or less than 0, okay? And so if we take a look at this polynomial inequality right here, x squared minus 7x plus 10 greater than 0, there's points to where the function goes from above the x-axis, which is greater, which is the solution, but then down here, it's not part of the solution set, everything that's less than 0, okay? And also, it wouldn't be part of the equation on the axis because it's greater than, not greater than, or equal to, all right? So that's what we're looking for. We're looking for where the function is going to satisfy an inequality. So to be able to do that, we're going to have a process to where we find these boundary points, okay? I'm going to call them critical values on occasion as we go through. So first thing we're going to do is we're going to set the inequality either less than 0 or greater than 0, or less than or equal or greater than equal to 0. Then we're going to find the zeros of the function. Okay, we're going to call those the boundary points. We're going to create a number line that's going to divide them up into intervals. Then we're going to find some test values, and these are values that are going to be within each of the intervals. If the value of f is positive, okay, then that means that the function is going to be positive for all values in that given interval. Okay, so when we create up the number line, we're going to divide it up into intervals. And then if we go through and f at x is negative at that test value, then what's going to happen is all the values within that interval are going to be less than 0. So the behavior is going to be predicted by that test value, or it's going to be the same as, right? Finally, we're just going to write the solution set, and then we're going to go ahead and write it in interval notation. All right, so let's take a look at a couple basic examples of this. We have this x plus 2 times x minus 3 is going to be less than or equal to 0. Okay, first thing, set it equal to 0, already done for us. Next thing, find the zeros of the function. Well, that's pretty easy because we would have x equals -2, and we would have x equals 3, all right? And we would get that by just setting x plus 2 equals 0 and x minus 3 equals 0. So clearly we can see -2 and +3 for our boundary points, okay? So once we set those equal to 0, those are our boundary points. Okay. Again, I might call them critical values in this case. So now what we're going to do on the number line is we're going to have 3 intervals. Okay. So we have a -2, we have a +3, and certainly we have 0 in here. And so we have 3 intervals. We have one from -infinity to -2, and it should include it because it's less than or equal. Okay. So if it's less than or equal, we're going to put a solid dot there. We have another interval. All right, and I'm going to put a bracket here because it's inclusive. We have another interval from 2 or -2 to 3. Right? And then finally, we have a third interval from 3 to infinity. Now, what I'm going to do is I'm going to make a table that has all of these intervals, and then I'm going to pick some test values, and I'm going to go ahead and I'm going to see what happens when I substitute the test value back in. Okay, so our intervals, one, like we said, -infinity to -2, and a test value that occurs in that interval is going to be -3. Right? Another interval that we had was -2 to +3. Now I'm going to pick 0, and we should always try to pick 0 whenever we can, because that's one of the easiest numbers to work with. And then finally, the last interval that we had was from 3 to infinity. Might as well just pick 4, okay? And always try to pick numbers that are easy to work with, okay? Now what we're going to do is we're going to see what happens when we substitute these test values back into the inequality, okay? So our inequality All right. And remember, our inequality was x plus 2, x minus 3 less than or equal to 0. All right, sorry, I had a mark on my screen. Okay, so that's just the original problem. And so if I substitute -3 back in, I get -3 plus 2, and then I get -3 minus 3, all right, less than or equal to 0. And then if I simplify that, that just gives me -1 times -6 less than or equal to 0, or that gives me 6 less than or equal to 0, which is clearly false, okay? So the last thing we determine is this interval going to be in the solution set or out? Okay, so I'm going to say in or out, and because it's not true, it's going to be out, okay? Now we're going to do this again. We're going to substitute 0 back into the inequality. So we get 0 plus 2 times 0 minus 3 less than or equal to 0. We get 2 times -3 less than or equal to 0, or -6 less than or equal to 0. And that's true. So that's in, which means that this is part of the solution set. We still have to check the last one. Okay, so let's check and see if 4 works or does not work. So we would have 4 plus 2, 4 minus 3 less than or equal to 0. That gives us 8 times 1 less than or equal to 0. And 8 less than or equal to 0 is not true. So this is out. So the solution set for this is going to be from -2 to +3 inclusive. And again, it's inclusive because of this less than or equal to. Okay. So technically, we should say that x is an element of this for the solution set, but no big deal if we don't write that. Okay, so that's how we go through and solve one of these basic sort of inequalities. Now, in the remaining videos, we're going to take a look at some more difficult types of these, but for right now, we just want to make sure we understand the process.